Right, guys, I haven't plugged the iPad in yet, but I'll leave that now. Could you all comment your names, please? Didn't ask. Yeah, everyone comment your names and I'll also do the register. And also, can you guys tell me if you have seen... Oh, no, that's the wrong folder. Hang on, back. Have you guys seen this before? So I can't remember if we did this together, whether I did it with my second years. Hopefully we haven't, because it's a good sheet of questions, but if you've done it, you've already done it. So I'll just wait there for that to open for a second. There we go. Do you guys recognise this? It's a sheet of really horrible integrals. Just have a look at that for a second, just while I do the register. Right. Right, Alex, hello, Joanne, Fifi, Sophie, Roddy, Callum. No, it's not the 66, Becca. It's not the 66 integrals. It's some really horrible, lots of them are like double substitutions, so you got to do a substitution and then do another substitution a bit later on. Okay. Yeah. All right. Well, we'll give these a go. It sounds like even if we have, you guys can't remember them. They are horrible. We will. I reckon we can get 20. Can we do 20 in one lecture? We can try. We'll start at the top. We're basically going to work our way through these today. Are there any other topics you guys have identified that you want to do tomorrow and Friday? Because I think if we just stick to integration, it might be a bit boring. Let me get some white paper up so I can block out half of them. I'll do. So it starts off easy. The first three shouldn't be any trouble. So we'll start with these three. I'll give you guys 2 minutes an integral, so 6 minutes for those three. George, yeah, I'll swap you in now. We need to do the skills check today, I just remembered that, so I'm going to write that on my desk. Some skills check. Cool, but if you guys would like to get started, 6 minutes on the clock starting Sorry, I just stuffed my face with chocolate. Yeah, okay. So Fifi can't do the first one. Roddy's struggling with 3. Okay. I've opened the team's chat, so if you guys could send me answers. I might give you a little bit more time, but I will give you some hints. So the first one, I would use reverse chain rule. But you could also do this via substitution. So there's a couple of options with this one. So reverse chain rule, because we've got a function to a power. So we've got a function nested inside a function. We've got a composite function. So we know the thing is going to have a power increase to 6. So we're going to get 4x minus 9 to the power 6. Because we raised the power by 6, we're going to have to divide by 6. And now if we differentiate this, the 4 would jump out the front. We don't want the 4 out the front either, so we need to divide by 4. 4 times 6 is going to be 24. So we need 1 over 24. 4x minus 9 for the 6. Let's see. So that's how I do it by reverse chain rule. Remember, we're thinking about inside and outside. If you wanted to do it via substitution, you could say u is 4x take 9. So du dx is 4. So dx is du over 4. And then we would get u to the power 5 du over 4. Integrate that, we'd get u to the power 6 over 24 plus c. And put x back in, and we end up with the same thing. So that's how you do the first one. We'll check your answers in a minute. The next one. Again, we could do this by substitution. I'm going to do it via the inverse chain rule again. So I'm going to bring the bottom up to make it integral of 5. 4x take 9 to the power minus 3. Then it's the same idea again. Power's going to go up. So we're going to get 4x take 9 to the minus 2. I need to divide by the power, so divide by minus 2. So we're going to get minus 5 over 2. And then I also need to divide by the 4 that would come outside. So I need a 4 on the bottom, so that's going to be 5 over 8. 4x minus 9 to the minus 2. And you can do the same thing by substitution very quickly. So you got u is 4x take 9. Same thing again, almost identically. You work it all through, and you guys can do that one, but it's the same kind of idea. All right, last one is a partial fraction question. I can tell it's partial fraction because the bottom bit is a difference of squares. So we can factorize the bottom to get 5x over 2x minus 3, 2x plus 3, which I'm going to turn into a over 2x minus 3 plus b over 2x plus 3. So skipping a couple steps, we get 5x equals a, 2x plus 3 plus b, 2x minus 3. Let x equal 2/3. Which will give me 10 over 3 equals, wait, do I want 2/3? Or is it 3 over 2? Should be 3 over 2, sorry, forget that. Let x equal 3 over 2. Got my fraction upside down. So we get 15 over 2 equals 6a. So a is 15 12ths. For b then, I can let x is minus 3 over 2. So we get minus 15 over 2 equals minus 6b. So b is minus 15 over 12. Cool. All right. Okay. So my integral becomes the integral of 15 over 12 lot 2x take 3 minus 15 over 12 2x plus 3. Now we can actually do the integral. So we're going to get 15 over 12 ln 2x take 3. Because of the reverse chain rule, that 2 that's inside the log needs to come underneath. So we're going to get 15 over 24 ln 2x take 3 minus, same thing again, 15 over 24 ln 2x plus 3. And I could take out 15 over 24 and then get ln 2x take 3 over 2x plus 3 all in brackets. So that would be my preferred form of an answer. Is that there? Cool. Let's have a quick look, see what you guys did. So, Roddy, what did you do, Roddy? You forgot to integrate the first one? Okay, the first one is a bit of a mess. Second one, you divided by 4, but you forgot to divide by the minus 2, so that's not quite right either. I'm just trying to work out what you did with the second one. You got 5 over 4, interesting. Where did I get negative? I'll check that one through in a second. We'll move on for now. But, and then Becca. Yeah, I might have made a mistake in 3. My 15 over 24 might be wrong. I'll check over that one while you guys do the next one. Yeah, because you've all got 5 over 8, which does sound a bit better. Oh wait, we got the same thing, but just different ways of doing it. Oh yeah, no, you are right, aren't you? Cool. Okay, so they're equivalent. Cool. Right, I'll reveal the next next view. The drawings. Here we go. So they look kind of similar, but they are all different. And they are labelled completely wrong, so let's change that to 4, 5, 6. Could you guys try these 3 again? I'll say 7 minutes. They are getting slightly harder, so 7 minutes starting from now. If you need any hints, just ask. But yeah, give it a go. Right, VP has done the first one, somewhat, and no one else replied. It's a good thing we're revising integration, isn't it? Maybe we should just do this all week. So yeah, first one, difference of squares. Well done for spotting that. So, 5 over 2x plus 3, 2x minus 3. So we'll have a over 2x plus 3 plus b over 2x minus 3. So 5 equals a 2x minus 3 plus b 2x plus 3. Again, let x equal third and 2/3. Sorry, x equals 3 over 2. And x equals minus 3 over 2. So we get 5 equals 6b, so b is 5, 6, and also 5 is minus 6a, so it is minus 5 over 6. So let's put that in up here. I'm just going to erase a and b and write in 5, 6 and minus. You could expand it if you want. It's up to you guys there, really. So that's what we're trying to integrate this time. So integral sign, so we're going to get minus 5 over 12, then 2x plus 3, plus 5/12, then 2x minus 3. Alternatively, you might have, will that be 12x plus 18? So you might end up with 5 over 12, then 12x plus 18, plus 5 over 12, then minus 18. So you might have that, they're the same thing. Still more if you've expanded it. And then you could take out 5/12 and you could use log rules to simplify. So that's that one. Alright, let's have a quick look and see how you guys did with that before we get on to the harder two. So Alex, you've done the first one. Yep, cool, I agree. Nice. Sophie. Yep, good. Doesn't look like anyone's got anywhere with the next one though. Yeah, so if you think you got a sign error, maybe not. Yeah, your A's and B's are the wrong way around. I think your A is over the B term and your B is over the A term. Always label them. I think that's what you've done wrong there. So right, next one, you got the integral of 5 over 4x squared plus 9. Now, this I think is going to be quite horrible. So, did anyone work out how to do this? Because I want to see if any of you guys can figure this out before I give it away. And we're kind of excited. I haven't looked at the answers to these. I'm going to have to work this out too. But I've got a feeling of what it's going to be. So I'll try and talk you guys through that so you can work out how we're identifying what kind of integral it is. Any ideas? Any suggestions from anybody? Okay, so let's go through our list. Is it something we can do via recognition? Let's have a think. If we were to do this via recognition, we need to pull the bottom bit up to the top. So we'd get 5 brackets, 4x squared plus 9 brackets to the power minus 1. but you can integrate like a learn of a learn. Okay, imagine don't go down that pathway. Okay, so it's not going to be recognition. Is it by parts? Can you see parts? No, there's no other parts to it. What other methods were there? It's not partial fractions. We can't split it up. So you eventually get to the point where you're left with substitution. Okay, what could we substitute for? Is the next question. And I feel like this is going to be a trig substitution, but I'm not entirely sure. Yeah, but basically, I'm thinking the bottom. If we can turn it into like tan squared plus 1, then we can turn that into sec squared, bring that up to the top, and then we've got cos, which we can integrate. So often when you've got like x squared plus a number, it's usually some kind of trig substitution. Problem here though is you've got the 4 and the 9. So I think I've got it. It's going to be a weird substitution. So I basically want to turn the bottom of this into tan squared x plus 1. Yeah? And then I can turn that into sec, and then we're away. We're sorted. Or, sorry, it'll be tan squared u. Can anyone spot how I can do that? How can I, what can I substitute that's going to make this work? So the reason this is going to be really hard is because we've got a 4 there, and we've got a 9 there. So if I wanted to, let's think. All right, let's take out a factor. How do we even come to that conclusion? I know it needs to be a substitution, and a standard trig, so a standard u equals x substitution isn't going to get us anywhere. It's basically a pattern. If you can see that you've got something that's going to be a trig plus 1 or something like that on the bottom, it's kind of, you just get used to spotting that it's got to be trig. I know it's like looking, the next one there is probably going to be trig as well. So yeah, if I take out a factor of 9, we could say this is, and I'm going to pull it right outside the integral just to make this look a bit nicer. So we'll say it's 5/9 integral 1 over 4 over 9 x squared plus 1. I think this will work. Okay, so if I want to get rid of the 4/9, I could say we could say that that's 2/3 of x all squared plus 1, just that bit on the bottom. So I could say 2/3 of x equals tan u. So that would be my substitution. So in other words, I could say x is 3/2 tan u. Yeah, I think this is gonna work out quite nicely. So got my substitution that x is 3/2 tan u. If I differentiate that, so if we go back up to the top, there's my substitution. X is 3/2 tan u. Get rid of this. Differentiate it to get dx du. What does tan differentiate to again? Anyone remember? It's been a while. I might have forgotten. Tan differentiates to what? Anybody? It's going to be an awkward minute of me waiting for you guys to answer otherwise. Differential of tan is what? Come on, guys. One of you must be able to know what the differential of tan is. Even if you have to Google it, surely one of you remembers what tan differentiates to. Something, yeah, it does something. Come on, it's going to be a type of trig. You could do it by recognition if you wanted. You could use the sine over cos. Yeah, sec squared. Thank you, George. That was painful. It goes to sec squared u. There we go. Good. Yeah, everyone's doing it now. Good. Okay, so dx du is 3 over 2 sec squared u. Okay, let's put x in there. So if I put x in as tan, we're going to square that. The 4/9 will cancel with the 9 over 4. So our integral will become 5/9 integral 1 over tan squared u plus 1. And dx then will be 3 over 2 sec squared u times 3 over 2 sec squared u du. Cool. All right, so let's do some simplifying. So if I times it out, we're going to get 15 over 18 integral of sec squared u over tan squared u plus 1 du. What is tan squared u plus 1? How can we rewrite that? I think I said it earlier, actually. Tan squared u plus 1 is sec squared u. So the whole integral turns into the integral of 15 over 18 du. Which is going to give me 15 over 18 u plus c. And we can now rearrange to get u. So I know that x is tan u. So 2/3 of x is tan u. So u equals arctan 2/3 of x. So I could say this is 15 over 18 arctan 2/3 x plus c. Cool. Right. Bit as hard, but hopefully doable. You guys probably will be able to do 6 now on your own. It's very similar to this. Similar kind of substitution. You might get something else as an answer. So I'll give you guys a few more minutes. 4 minutes to do question 6. And the timer will start. What do we say? So does the integration get even harder? Alright, these are further maths integrals that we are doing with non-further maths methods, which makes them seem super hard. You'll learn some further maths methods that make these kind of easier to do. So further maths isn't necessarily harder, it's just more maths. It can be a bit more challenging, but you guys are good enough to cope with it. I wouldn't worry. It's fine. If you found complex numbers and matrices okay, and you found the A-level maths okay, it's not going to be much worse. There'll be a few hard topics, but overall it's just more maths. So yeah, don't worry. Photo math. What? Did I say photo? Further. Yes, you can. Yeah, there's a few that will work on both, and you are allowed to use them. Anyway, let's do this. So I think a couple of you have sent me your answers. So it's the same substitution. X equals 2/3 3/2. X equals 3/2 tan u. So dx by du 3/2 sec squared u. So we get the integral of 5 over the square root of what's it mean, 9 tan squared u plus 9 times 3/2 sec squared u du. So you get that. Right, so the bottom, I'm going to take out a factor of 9, square root it, which will give me a 3. That 3 is going to cancel with this 3, so I'm going to cancel out those basically. The integral is going to become the integral of 5 sec squared u over the square root of tan squared u plus 1 du. And yeah, tan squared u plus 1, as we saw just now, is sec squared u. The square root of sec squared u is sec u. So we're going to get 5 integral sec squared u over sec u du. Sec squared divided by sec is just sec. So we're just talking 5 integral sec u du. Okay, the integral of sec is one that I might have forgotten myself. I think it's ln sec plus tan. It's in the formula book. I'm going to write that down and then I'm going to go Google it. 5 ln sec plus tan. That does seem like the right thing. Let's Google it. Integral of sec. Integral of sec is, drumroll, ln of tan plus sec. Oh yeah, cool, it is right, good. So that's my answer. We need to put x back in though, so if I untan this, we're going to get 2/3 x is tan u, so u is arctan 2/3 x. So it gives me this really horrible answer. So we'll get 5 then sec arctan 2/3 x plus tan of arctan. That didn't cancel out. Tan of arctan of 2/3 x is just going to be 2/3 x, I think. Yeah. So we get that. Cool. What do you guys get? Let's have a look at your answers. If you wrote it, so start. Callum, what did you do? Yeah, you can't use learn when it's power half like that. I'm wondering if there's an easy way to do this actually. Could I bring that path there? No, that is how you do it. No, sorry, Callum, yours is completely wrong, I'm afraid. I like the bit where you took route 4 outside. Other than that, though, there's not much correct in there. Roddy, question? No. Anyone got any questions? This is horrible, but substitution is not always easy. Right, I'm gonna start clearing the screen, so I don't see any questions. We'll do some more of these. What's Joan saying? If 4 months on something, I've got more chance of my band taking off, and that's all I'll say. All right, could you guys try these ones 6, 7, and I'll label this one 8 because it's whoever labeled these is not very good at numbers, ironically. There you go, 6, 7, and 8. If you guys could give those a go, say 10 minutes this time. Starting now. All right. Sophie, your first one was right, but you didn't finish it. You differentiated the answer instead of integrated it. So for your second one, you differentiated it again. You got right to the end and differentiated it. So close, but no. George, looks pretty good actually. Yeah, I'll have a closer look in a minute. Callum, yours upside down. Thanks for that. I'm not gonna go all the way around. If you could resend it, that'd be good. Becca, that looks pretty good. All right, let's go through these. So you guys have got so much. First one is double angle formulae. Because remember, if you've got 2 sine x cos x, that's the same as sine 2x. So here we've got sine 2x cos 2x, so we're going to get sine 4x. So the whole integral turns into integral of sine 4x. Then we can integrate that. Sine integrates to minus cos, so we get minus a quarter cos 4x. That's C for the first one. So that's it. Please stop and ask questions if you need help, guys. I'm going through these quite quick. I think we will spend tomorrow on this as well, because you guys can use practice. Number 7. So we got 2 sine x cos x, which is a double angle on top, but I think that's a trick, because you've got 1 minus cos squared on the bottom. 1 minus cos squared is sine squared, so I can say this in the integral 2 sine x cos x over sine squared x. I can cancel the sine on top with the sine on the bottom, so the whole integral becomes integral of 2 cot x, and cot integrates to ln sine x, I think. So 2 ln sine x plus c. I'm going to need to check that. Again, it's one in the formula book, so I've not learned it properly. Ln sine, I think it's ln sine. Ln sine, yeah, it is. Good. Cool. Right, and the last one is a recognition question, because we've got a function to a power times the derivative of that function. So remember, this is of the type f of x to the n times by f dash of x, and for this you try fx to the n plus 1. So we're going to try cos to the 8. So if I differentiate cos to the 8, we'd get an 8 out the front, so we don't want that, so we need an 8th. And cos differentiates to minus sign, so I also need a minus, but then that's going to be my answer. 1/8 cos to the 8. Cool. So Becca, you had a sign error, I think, there, because cos differentiates to minus sign. Callum, yours upside down, so I don't know. George just needed a sign there. You differentiated cos and got sine, it should be minus sign. Yeah, you can say the last one you can actually do via substitution as well. You could say u is cos and do it that way. Yeah, cool. Right, we've probably got time for one more set of questions. What's going to be next? Ooh. Alright, I'm going to give you guys a hint for the first one. I'll leave you with that hint, and I'll put and repeat. We have done one like this, but been a while. Question 11 is similar sort of thing, and then 12. 12 is recognition. So 12 is the easiest one. 10 and 11, a bit more time consuming. I'll give you guys 10 minutes and we'll see how you do. How is that helpful? Okay. I will do the first one for you. And then you guys can hopefully get the second one done on your own. So, I'm going to say integral of cos to the 7 is cos squared times cos to the 5. And the reason I'm doing this is because cos to the 7 I can't integrate. I need to mix it up. I need some signs in there, otherwise I can't use recognition. So I'm going to change the cos squared into sine. So I'm going to say that's 1 minus sine squared times by cos to the 5. Then I'm going to expand that. So we're going to get cos to the 5 times minus cos to the 5 sine squared x. And then I'm going to split those cos to the 5's up into cos squared times cos cubed. So we get cos squared cos cubed x minus cos squared cos cubed sine squared. Then I'm going to do the same thing again. I'm going to change all the squares into sines. 1 minus sine squared cos cubed minus 1 minus sine squared cos cubed sine squared. Then I'm going to expand it. Cool. Alright, then we're going to go again. So the middle two terms are actually the same thing. So I can slightly simplify this and say it's cos cubed minus 2 sine squared x cos cubed x plus cos cubed x sine to the 4x. Right, I'm going to go right back up to the top because I need all this space back. So if you guys want to rewatch this one, you can just check through it again. Right, so one last time I'm going to change it into cos squared times cos minus 2 sine squared cos squared times cos plus cos squared times cos sine to the 4x. And then all those cos squares I'm going to turn into 1 minus sine squared. Go and expand it all. So I'll do this in red because it's our last step. So cos x minus cos x sine squared x minus 2 cos x sine squared x plus 2 cos x sine to the 4x minus sine to the 4x cos x plus sine to the 6x cos x. And this will simplify a little bit. So we got cos. We actually got 3 of those terms. 1, 2, 3, yeah. We've got 3 of those terms and 1 of the last term as well. So last thing, write it all out simplified. So this becomes the integral cos x minus 3 cos x sine squared x. We've got sine there. Plus 2 minus 1, so plus cos x sine to the 4x plus cos x sine to the 6x. So we get to this point. Now we're all ready to integrate it. So now we've basically got a load of sets of recognition. Cos integrates to give me sine. For the next term, we're going to try sine cubed. If we differentiate sine cubed, we get 3 down the front. We get cos down the front. We just need to introduce a minus. For the next one, we're going to try sine to the 5. If we try sine to the 5, yeah, it gives us cos. That's fine for the sine. But we need to divide by that 5. And the last one, we're going to try cos to the 7. Oh, sorry, try sine to the 7. And we'd get a 7th, so we need to get rid of that as well. So I make it this. I feel like I've made a sign error somewhere here. I feel like it should be plus minus, but whatever. There we go. That's roughly how you do it, though. All right. Yeah, it takes a while. Normally, you'd never see 1 to the power 7 in the exam. So for the next one, same kind of idea. So for the next one, for 11, I would just times each of these terms by sine to the 4, and then you can integrate it. So if you guys, I'd like you guys to try 12. We'll skip 11 because I've already done most of the hard bits. So if you guys could do 12, that one should just be a recognition question. But that's how you do any odd power of trig. You split it up, you keep splitting it. There are other methods to do these then. But I quite like these methods. It doesn't take that long. It's pretty easy stuff. Anyway, give 12 a go, and then we're going to try one more after that, I think. Yeah, this they wouldn't come up like this in the exam, but it's good. It's good practice. We're getting there. We're not doing too bad. So yeah, if you guys could try question 12, that'd be good. I'll give you guys 3 minutes to do that. Starting Cool. Right, so this one, I'll go for this quickly and call it a day. We're going to write it as sine cos to the minus 7. And we're going to try raising the power of cos. So we're going to try cos to the minus 6. So if we differentiate that, cos to the minus 6, we get a minus 6 out the front, which we don't want. Let's just rewrite this. So we're trying cos to the 6. I'll write it like this, it's a little bit clearer. So if we differentiate the inside, cos differentiates to minus sine, so we get a minus sine out the front. Okay, we want a sine, so that's something. If we differentiated the minus 6 bit, that's going to come down the front as well. Minus minus will cancel, so we'd actually get 6 sine cos to the minus 7. Which is very close. The only difference is we've got a 6 that we don't want. So my answer is going to be 1/6 cos to the minus 6 x. That should be my answer for this one. Cool. Right, so a little bit of recognition there. Okay, tomorrow then we'll do the progress check because I forgot about that. I need to check that's actually up, and then we will be doing. We'll try and get through the rest of these tomorrow, and then Thursday, we'll revise something different on Thursday. Cool. All right, cheers, guys. It's 9 to 4 though. Where? No, I was doing 12. 11 will take ages. 11, you rely on what we already did. Sorry, Roddy, I meant, yeah, do question 12, which is just sine, not sine to the 4. To do that one, to do 11, you would want to do basically what I did for 10 all over again. Which I'm not going to make you do because that'll take years. Alright, have a nice evening. I'll chat to you guys tomorrow morning. Cheers. Bye.